Hi there, I'm Dan Schwartz. I'm the chair of the Department of Chemical Engineering. It's a great pleasure to be here with you all tonight. Solar cells have been around for about 50 years now, but nobody has really developed the ability to make them cheaply enough and efficiently enough for them to be ubiquitous in our society. Christine Luscombe and Hugh Hillhouse are two of the rising stars at the University of Washington working just on that challenge. So it's my privilege to first introduce Hugh Hillhouse.
So first, thank you all for coming and spending your evening learning a little bit more about molecular engineering and sciences here at University of Washington. So I want to tell you a little bit about introduce you to sort of the energy problem, to what role solar energy is playing, and then ultimately what's going on here at University of Washington in terms of molecular engineering and sciences and how we can utilize this wonderful resource of solar energy that we have. You hear the word energy a lot. You know, if you watch your TV, you see some commercial and somebody says, I'm an energy voter. And you hear about the energy challenge and energy crisis. The one thing I'd like to maybe start off with is to note that it's really not an energy problem. Probably you remember this thing, the law of conservation of energy. Cannot be created or destroyed, only changed from one form to another. So there's plenty of energy around. What it is the value of the energy. Things like electricity are very useful. The energy in gasoline, natural gas, very useful. Energy like thermal energy, such as the thermal energy just right here in this air, not very useful, but it's still energy. So we talk about energy, but we need to keep in mind that when we use energy, what we're talking about is taking high value energy and turning it to lower value energy. And the rate that we do that is power, and it has units of watts. So you're going to hear the word watts a lot this evening. And so that's the rate at which we're turning high grade energy into lower grade energy. So what is the Grand Energy Challenge? So first off, before we can understand what the Grand Energy Challenge is, I think it's really useful to point out what is the very special role that energy, and in particular solar energy, plays in civilization. We have sun, light shines down, grows things, right? Now suppose we have corn, grass, whatever, and sometimes if we rewind the clock a long time ago to sort of the beginnings of civilization, you would have farmers tending a field, right? So farmer puts work into the crop, produces food, said farmer eats food, and if you think about how much energy we need to consume, so 1,700 food calories, which is, if you average it out on a 24-hour cycle and change the units to watts, that's about 80 watts. That's what it takes your average sedentary male to maintain body weight. If you eat more than that, you will gain weight. If you eat less than that, you will lose weight. Pretty simple. Okay? So if you do work on the field, well, you have to eat more food. Now, one of the things that is important about this is imagine everybody on planet Earth spent their day either growing food or hunting and gathering. Well, who would be around to do things like create all this technology we have around us? So the very sort of essential feature to note is that really food production and the role that energy plays in this is very vital to civilization itself. So if we think about, go back, 7,000 years and start looking at the earliest civilizations, whether it's the Euphrates Valley or the Indus River Valley or the Red River Valley. So all of these places developed ways to have one person generate food for more than one person. And what that allows is people to specialize. It means that these two burly fellas don't have to actually go out and grow their food. Okay? The other thing that's important to note is this energy that's in the sun, that is the energy that's stored in the sugars in the food. That's the energy that's in the carbohydrates here on the plate. And that is ultimately the energy that's in the glycogen in this fella's muscles to strike that hammer. It's all solar energy. So as civilizations grew and became more complex, that was enabled because we found ways to create more food and have one person create a lot more food than what they can eat. So we took this stuff here, oil, which is actually ancient solar energy. It's light that came down to the Earth's surface. It was in plant matter. It got buried, and with time and temperature, it got turned into oil. So we take and use this, put it in things like this, grow things like that, and get more food. And that allows us to create ever more complex things. Engineers get trained and learn how to build buildings. People learn how to make radios. We have time, people have time to pursue art, and we also create even fancier ways to kill each other. We now dump a lot of oil into farming, and this is our modern industrial agricultural system, and that is what enables things like this. And so this intimate connection is really about, how solar energy and ancient solar energy are directly connected to the complexity in society. It allows us to have teachers, to have doctors, and it's energy that also allows us to increase our standard of living. So how much energy do we need? How much power do we need to consume to have a good standard of living? So I mentioned 80 watts. That's what it takes on average for the people in this room to maintain your body weight. Because you live in the US, we'll take all the energy sort of usage of the United States and divide it by the people and normalize for time. And when we do that, what we find out is that each of us is indirectly and directly responsible for about 11,000 watts of energy usage. And this is defined by what you choose to buy, what you choose to drive, and all those kinds of things. Okay? So 11 kilowatts. So I think it's fair to ask, what do we get for that 11 kilowatts? So if we take and plot, take and collect how much energy does each average citizen use in all the different countries around the world, and plot the Human Development Index and the gross domestic product per capita as a function of the total primary energy usage per person. So we see the data in blue, Human Development Index, and this green data, that's the GDP per capita. And again, these are as a function of the total average energy each citizen uses. So there's the US. There we are at about 11 kilowatts. We have very high Human Development Index and very high gross domestic product. What's interesting is when you plot and you see what some of these other points are, something interesting crops up, and that's to look at places like Japan and Denmark. And they have very, very high Human Development Indexes and GDPs that are very close to that in the US. So what it says is that societies are possible where people on average use about 5 kilowatts, but yet have just as good of education, infant mortality, and gross domestic product as well. So what is the grand energy challenge? If you look at how population is growing, so different models suggest it might plateau somewhere between 10 and 12 billion people. So let's just call it 10 billion. 10 billion people, planet Earth. If we lived in a world where everybody used 5 kilowatts and they could have really high quality of life, that's 50 terawatts. Okay? So you're going to hear that word terawatt a lot. It's a very, very, very big number. Right? Right now, the US uses about 3.3 terawatts of energy continuously. And there's a scenario in the future where the planet needs 50. And hopefully we want to do that without wrecking the planet. Okay. So we have choices. We have choices about where do we get our energy. So US uses about, like I said, 3.3 terawatts. Let's look and show some things graphically. If you wanted to get 1 terawatt from nuclear power, this is how many nuclear reactors you would have to have. Okay? So your average nuclear reactor generates about 1 gigawatt of power. So we can see right here in Washington State. Okay, what about biomass? So we all know, and there's lots of great things going on where people are engineering molecules and different plants where we can grow things and then turn those things that grow into fuels, which we can put into our cars. But when you go through and calculate the numbers, actually plants are not a great way to harness sunlight. If you compare the best plant versus one of the worst solar cells, the solar cell wins like big time, okay? So you need a very, very large area of land to grow these things, and if we're going to turn them all into fuel, well, what do we eat? So biofuels are part of the solution, but it's not all of the solution. So what about wind? Well, if you wanted to create 1 terawatt from wind, you would need to cover these land areas with windmills, okay? And again, so wind is going to be part of the solution, but it's not all of the solution. Solar, 1 terawatt of solar could be gained with that land area. And there are actually quite a lot of places in this area of the country where it's very sunny and there's not a lot else there. No farmland, things like that. So the punchline is that solar has this huge opportunity to play an ever-growing role in how our energy economy evolves. Now, what are some of the flies in the ointment? And there are a few flies. This is the demand curve. And so basically what this is, I think this is for a county somewhere, Texas, I think maybe suburban San Antonio, I think, collected over a period of time and shown during the summer, so the axis here, these are hours, that's 1 day, 2 days, 3 days. So you can see how the demand from the power grid oscillates during the daytime. Okay? There it is in the summer, and here it is during the lowest demand time in the spring. So there's two things from this that tell you something. Well, the sun isn't out during the nighttime. So where do you get all of this power here at the bottom? So this is what people call base load demand. So that requires one of two things. You either have to have ways to store the solar energy, and there are really big unsolved challenges with that right now, or you have to have other things that are part of the mix. Okay. So, and those things, maybe it's nuclear, maybe it is hydro. It's one of the things that is really that Washington State is blessed with is wonderful, green, cheap power via our hydroelectric plants. So the Grand Coulee Dam, while it generates at max over 7 gigawatts, on average it's about 2.5. It's not, sometimes there's drought, or whatever, and you can't always be letting water flow through the dam here. Bonneville Dam gives about 0.6 gigawatts average, and the state's one nuclear power plant gives you just about 0.9 gigawatts. So it's really a great opportunity, even for solar here in Washington State, in the sense that there's a really great resource to satisfy that base load demand. Okay. All right, so what is, so people, I get asked this question, well, how come we don't use, so how come solar energy is not everywhere? I mean, there's not enough sunlight to power things or whatever. Well, that's not true. It's a big myth in the about solar energy. So this is a map, and it is shaded in color, indicating the intensity of light that makes it down to the ground. Right. So there's lots of things that factor into that. How far north you are, what's the latitude, how much atmosphere does the sunlight have to go through? Is it cloudy? How often is it cloudy? Notice that Louisiana gets much less sunlight than Arizona, despite the fact of even being further south. It just has to do with weather patterns and things like that. So what we find is the best places on Earth for solar energy tend to be things on the interior of continents, not near the equator, but sort of mid-latitude. Maybe a little bit in the southern mid-latitudes, but definitely not near the equator. So you look at this map, and the first thing most of you here in the room naturally did was you go, pretty colors, not so good, right? So so it's not the sunniest place in the U.S., but don't let that fool you. Look at the most developed countries. The U.S. has by far the biggest solar resource than any other industrial country. Okay? So if you look at this right here, you might get depressed maybe for just a brief second, but just hold on to that thought. Here's Germany on the same scale. And look what Germany did. In 2010, they installed 7.2 gigawatts of solar cells. Now, that's good news, right? What's the bad news coming? 2010, the entire United States installed less than 1 gigawatt. Okay? So, some questions there. Why? And how do we change this, and how do we enable a future where the U.S. can utilize this wonderful resource that we have? Okay, so what is a solar cell? So solar cell, I'm going to give you two versions. The first one is simple, the second one is less simple, but don't let the second version scare you. The rest of the talk doesn't get more complicated from there. Okay, so basically all a solar cell is you bring light in and you excite an electron to a higher energy level, and then instead of letting it fall right back down, you let it run through an external circuit, and that can run a light bulb, anything, right? Charge your cell phone, whatever. So for those of you who know what a semiconductor is, so we typically make solar cells out of semiconductors. These are energy levels that are filled with electrons. These are energy levels that are not filled with electrons. If you bring a photon of light in that has energy bigger than what we call the band gap, so there's no energy states here, it can excite an electron. Energy is conserved in that process. That happens very quickly on the time scale of about 10 femtoseconds. Very quickly, these electrons relax down to a lower energy level, generating heat. That's a loss process. Then they can fall down across this energy gap and emit a photon. Now, that emission of a photon, this is what an LED is. Okay? And all these new lights that are coming have LEDs. This is all the process is. Instead of exciting it with a photon, you excite it by applying a voltage, inject an electron here, and when it falls across that gap, it emits a photon. So a solar cell has a lot of similarity with an LED. So these processes are happening. Whenever one photon hits a solar cell, this process happens. If I hit the solar cell with a lot of photons, since the rate at which this step happens is slow, and I can hit it with a lot of photons really fast, I build up a concentration of electrons here and a concentration of holes. And what that does is it splits these two levels, which ultimately are related to the voltage you get from the solar cell. So I'm only going to make a couple of comments from here about this. The physics of what's going on here sets the ultimate limit for solar energy conversion with sort of standard physics, and it's about just shy of 34% efficiency. It means the energy and the light that comes down and hits your solar cell, you can get 34% of that in electricity, in principle. Now, that's not really what happens. No solar cells are that efficient. If you have anything going on here, an energy level, or I'll say this word later, a defect, that can cause this electron to jump back down more quickly, and these electrons don't go through the external circuit, and it's a loss process. So large-scale solar energy deployments are a reality today. So this is a relatively recent installation in Maryland. So this is a 16-megawatt installation. You can see the solar cells here, so you can see how they compare to trees and stuff like that. So this one installation alone saves about 17,000 tons of carbon dioxide per year. Right? So carbon dioxide is a gas. That's a lot of carbon dioxide. The U.S. is a very, people, they buy what is cheapest. People act in pretty much their own, in their own economic self-interest by and large and average. So if we want to increase how much solar energy people are using, we have to find ways to decrease the cost and make it competitive. We have to make it such that everybody in here wants a solar panel on their house, not because they know that it's a great thing to do, but because it saves them money. So how are we going to be decreasing costs for solar energy? So if we take a look right now at what are sort of the best numbers for adding new electricity generation capacity to the grid in the US, this is what we see. So right now, the cheapest is natural gas, and these are a combined cycle. And these are all numbers from the Department of Energy, and there's lots of assumptions behind each one of these numbers. But natural gas is currently, if you were going to add new capacity, you would do it, and you wanted to do it most economically, you'd do it with natural gas. Coal is a little bit more expensive. Hydro, the problem with hydro is actually similar to nuclear is we have found all the good hydro, the good and easy hydro around. There's not a lot of new rivers that you can go put a hydro plant on and try getting a permit for a new nuclear plant. So those things are not really included in here. So here's really the issue is that we look at solar, and this has actually come down quite a bit. It's probably more along the lines of 15 cents per kilowatt hour. But nonetheless, you can see that if you're just going to act in, do the thing with the lowest cost, you're not going to do solar. So there's one way we can take a look and plot things to try to understand what some of the key factors are here. So if this is the total cost of installing a solar cell, dollars per meter squared, and you put it out there and it has some efficiency in the sun, if you take this and divide this dollars per meter squared by how much light comes down at noon on a sunny day, 1,000 watts per meter squared, and you divide that by the efficiency, you're able to turn this into a number, which is a figure of merit, and that's the cost per unit power. It ends up that people really don't care so much about the cost per unit area or about the efficiency of the solar cell. What everybody really wants is they want electricity and they want it at low cost. Okay? So these are the lines that are most important to move across. So if we make some assumptions about how much light comes down, how long your solar cell lasts, you can turn these initial capital costs into ongoing costs for electricity. And we can start plotting what is the current cost of solar energy on this. So there's how much, that's the manufacturing cost for a typical silicon solar cell, which is some of the default technology out there today. Presumably the people who make it want to make a profit when they sell it, so you have some selling price which is higher than the manufacturing cost. And you have to have it installed and have frames and all sorts of other things. And so this is the actual cost to the consumer, and as you can see out here, somewhere around 15 cents per kilowatt hour. There's one of the more famed US solar companies, SunPower. They make the most efficient modules, solar modules available on the market today in any country. And we also have, as a US company, the company that makes the most inexpensive solar cells out there for solar. So they're less efficient, but you can see that it's further across these lines. So the cost per unit power is cheaper for this than this, even though this is nearly twice as efficient. So it's not really so much a matter of efficiency, it's the blend of efficiency and cost. Okay, so that's the limit, the Shockley-Queisser limit. So when I walk through the slide with all the different physics going on, that's where that defines that upper bound. This is the region that we need to be aiming for. If we want to make it such that solar energy, that you see solar cells all over everything, everywhere, this is the region we need to be in. And that's what a lot of folks, a lot of people here, graduate students, postdocs, professors at the University of Washington, and across the globe are all shooting for, is to try to develop new technologies that can get into that region. So one of the things, a big something that's very important to the things that are going on here at University of Washington is that we're developing ways where we can make solar cells, but make them with things that are printable, right? Solar cells, if you've ever seen a solar cell, most likely it was crystalline silicon, and it was something that looked like a big blue or black wafer that was rigid, okay? Well, if we can develop techniques where we can take flexible substrates and print things on them, then we can dramatically reduce the cost and enable a different future for solar energy. So currently, roughly 200 million square feet of just Wall Street journals printed every day through machines like this. And so if we can take and adapt that kind of technology to printing solar cells, that's going to be a great thing. And how do we do that? Well, one of the keys is molecules. So one of the central themes in my group and in a lot of other groups is to develop new kinds of molecules that we can print with. I'm going to talk to you about things like this. So this is you can see a certain kind of molecule here. This is an inorganic molecule that is bound to the surface of a nanocrystal. And we make inks. They look like ink. They're black, liquid, and make things that might be composed of molecules like this or maybe composed of nanocrystals capped with molecules like this. There's other kinds of molecules, organic molecules, that Christine Luscombe is going to tell you about here in just a few minutes. But all of these things have a uniting theme, is that we're basically developing a new molecular science and engineering to use them where we can create inks that we can coat on substrates and do it cheaply, and so that we can enable solar cells that are going to be economic. Okay, so this is actually a very high resolution. It's a transmission electron micrograph, but it's just a high magnification image of some of the nanocrystals that we make in my lab. You can actually see, so there's the ink itself. You can see it's jet black. Those are the individual atoms that you see there, okay? And these nanocrystals, they have maybe only, say, about 10,000 atoms in them, which is about the same number as an organic polymer molecule or a large protein. So these things are really in the realm of they have defined shape, and they are molecules, okay? So we make inks like this. And the trick is how do you actually make an efficient solar cell out of them? So you can kind of think schematically about what we do is we spend a lot of time developing chemistry. You can think about it, just like a cook in a kitchen. We mix certain things for a certain time and temperature, control the environment, make nanocrystals, coat it on a substrate, and then basically these are the nanocrystals. One of the things that we found actually very useful to do is after we have the molecules or nanocrystals on the substrate, we actually then destroy them and create a bulk layer. So that at the end of the day, we end up with something that is very similar to a conventional solar cell, but we got there in a very unconventional way. Okay. So this is actually some photographs from some of the things from our lab. So we start with a substrate. There's our ink. We spread it on the substrate. We throw it in the oven. We put another layer on top of it with just a different liquid solution that we dip it in. That's the finished solar cell. Those are 6 different devices, all on a little substrate about that big. 6 different solar cells made from this molecular ink. So we've developed technologies like this. So we've developed devices that are about 12% efficient that are made from things like copper, indium, gallium diselenide. So that's the material that we ultimately end up with. So these are pretty robust. One of the things, though, that some people have concern about is if you start thinking about, hey, I'm going to build, suppose you're an investor, and you're going to build a factory that manufactures solar cells. Well, to get the economy of scale, it has to be a big factory. And it might cost you several $100 million to build that factory. And it's going to have to chuck out solar cells for a long time for you to actually get your profit. That means you better be pretty sure that you're going to have the feedstocks to put into your factory to be able to create the cells. So this brings to mind the issue of abundance of elements. This element right here, indium, it's in this screen. The more fascinated we become with touch screen devices, and these things have indium in them. So what it does is it brings some fear about the future availability and price volatility of things like that. So what do we do with that? So if we start looking at the relative abundance of elements in the Earth's crust, so this is a logarithmic scale of relative abundance of the elements versus atomic number. The technology that I mentioned, First Solar, the solar company that makes the most inexpensive solar cells, they use cadmium telluride as their absorber layer. And as you can see, tellurium is one of the rarest elements in the Earth's crust. And so people already have calculated, if we go back and think about terawatts, is there enough tellurium in Earth to make 50 terawatts worth of solar cells? No, there's not. So that's a problem. So we start looking for other elements. Well, what about these others, this copper, indium, gallium diselenide? Copper looks good, gallium looks good. Selenium, it's a little low there. This is logarithmic scale though, so if you just go up one notch, you're an order of magnitude more abundant. But I shade indium red not because there's not enough out there, it's because it's such a wildly useful element. And we find it so useful for so many of our technologies today. So, what are other choices? So we've been developing molecules and nanocrystals based off things like copper, zinc, tin, and sulfur. And so basically we have developed molecules, molecular inks, and nanocrystal inks that allow us to make devices, solar cells, out of this very, very cheap and abundant copper, zinc, tin sulfide. And so here's a device that's about 8.5% efficient. Now, one of the things that this is not on a flexible substrate, and I'll come back to that. So what are some of the grand challenges if we think about molecular science, and particularly with these inorganic types of solar cells? Well, the first is discovering new molecules, new inks that we can turn into solar cells that are efficient. It's easy actually to go and create a nanocrystal or create an ink that has the elements in it that will eventually combine to make a semiconductor. There's a near infinity of different combinations that will give you that. But only a very, 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 very small fraction of those formulations will make a semiconductor that is pure enough and that doesn't have defects in it that cause those electrons to recombine. Remember the complicated picture I showed you where the electrons build up in the conduction band? And they have to run through an external device. We want them to run through our lights, our battery chargers, or whatever. If they recombine through defects, game over. So the problem is how do we identify what those molecules are and synthesize them and create inks out of them that will make efficient solar cells? Part of that is what I refer to as taming the defect chemistry. Nature is the way it is. The laws of quantum mechanics and the periodic table, these things all they're fixed and we can't change it. So there are answers out there for what will make wonderful inks and wonderful solar cells. And it's already encoded in the laws of nature. It's a question of can we find it and can we use our knowledge of chemistry to know where those great spots are. Don't be rigid. So this is a big one. I mentioned these wonderful devices that we've already developed from these very earth-abundant elements, these inks. But thus far, we have to heat them to over 450 degrees Celsius to get them to work, which means you can't put it on a sheet of plastic. Now, people are developing polymers and plastics, different synthesis routes, developing new molecules that we can turn into flexible things that you can heat really high. But at the time being, this is huge because glass is actually not that cheap. It can add 5 to 15 cents per watt to the cost of a device. So, and you also can't run glass through one of these big printing machines. So there's a lot of molecular science and chemistry going into trying to make these things flexible. A special paintbrush is what I call it. We're not there yet. We probably won't be there for at least not 5 years, but we're developing a suite of technologies in chemistry where ultimately you could have, so some of you have, painted a room in your house and use one of these rollers, right? Dip it in the paint and then roll it on. Well, imagine a very special version of that where one roller is applying an ink. And then right after that, there's actually a little array of lights that shine and heat up what you just coated. That's the heating step. And then another roller that has a different ink, and another roller that has a different ink, and that you could ultimately roll it over a surface. Now, it's a long ways off, but you can just imagine what that lends itself to, and I think that ultimately is something that will happen. Multi-junction architectures. Going back to that complicated slide, that limit of 34%, the Shockley-Queisser limit, that's only if you use one semiconductor or one type of molecule that captures all of the light. But if you can develop different molecules or different semiconductors and have one of them capture some of the light and the other capture some other light, basically that's what we refer to as a multi-junction architecture. And there, the ultimate limit for efficiency is 86%. that we have, it is within the thermodynamic limits and within feasibility that here on Earth we could take light that comes down from the sun and turn it 80% of that, 86% of that energy into electricity. Okay? But it has to be done with multi-junction architectures, and that brings up a whole new suite of challenges and problems. So what are some of the things that we're doing to address some of these challenges? So there's a program from the U.S. Department of Energy. It's called the Sunshot Initiative. It is part of a strategic initiative in the Department of Energy to support research that will dramatically lower the cost of solar energy. And here's one of the projects that we're doing with the Department of Energy. So basically we're coming through and identifying a bunch of different molecules and nanocrystals, but then using combinatorial techniques to create spatial gradients of these molecules, combining different molecules in different concentrations. And on a single substrate here, we can make tens of thousands of different compositions. And then come through and use high throughput screening techniques to see what spot lights up. It's a little bit counterintuitive, but the spot that, when you shine light on it, the spot that shines light back at you is actually the good spot. It's emitting light just like a light emitting diode, which means we've turned off all the other recombination mechanisms. So this is one of the projects. In another project, which we're really excited about, we just got word of this. The National Science Foundation made an award to the university. There's a bunch of us involved in this, but it's called the Sustainable Pathways to Terawatt Scale Solution Process Solar Cells from Earth Abundant Elements. The crux of this is to go through and do all of the sort of the molecular science and engineering to develop inks from these. I mean, this is where these elements come from. Copper comes, one of the big sources of it is chalcopyrite. It's copper ore. The zinc comes from stalerite, which is zinc ore. And this is tin oxide. It's the tin ore. Sulfur, people used to actually mine it, but actually now most sulfur comes as a byproduct from natural gas and oil processing. So we take all these elements, we make inks, make the solar cells. But that's really doesn't really capture the essence of the project. The essence of the project is this, is looking at everything as a system. Ultimately, these things come out of the earth, and whether we like it or not, ultimately some of these things are going to get thrown back in the earth, whether it be in a landfill or something like that. And all along the way, there's chemistry to purify this into zinc, and then chemistry to turn that zinc into zinc molecules, and chemistry to turn those zinc molecules into precursors for the solar cell, or to make a nanocrystal. So all these steps involve taking some things from the environment and emitting things back into the environment. And so there's a large team of folks, including folks looking at sort of the environmental ramifications. So David Eaton, Alison Cullen is looking at some of the risk and policy decisions associated with how to make this whole system work. Scott Dunham is a professor in electrical engineering working on some of the theoretical aspects of the electronic structure and the quantum mechanics behind these things. And David Ginger and Daniel Gamlin are in chemistry, Xiaodong Xu from physics, myself and Christine Luscombe in school materials science and engineering. So with that, it just highlights the fact of how a lot of these problems are really addressed by teams of faculty and graduate students working together. And there's a lot of folks here at the university working on that. And so it's my pleasure now to hand over the laser pointer here to Professor Christine Luscombe, who's going to tell you about some of her work on organic inks.
So I'm going to be talking a little bit about my work related to using polymers instead of nanocrystals in solar cells. But before I do that, I want to start off by just reiterating some of the things that Hugh just mentioned. So the first thing that he mentioned is that for civilization to grow, or for our societies to continue growing, we do need to put in more energy. And I just want to show you one example where that did actually go wrong earlier in the year. So during the summer in India this year, they had major blackouts, where 360 million people were left without electricity. And if you think about that number, that's actually a huge number. The US population currently is at around 310 million people. So that number of people going without electricity is similar to something like this whole country coming to a halt. So the problems that they had, they didn't have electricity, so none of their traffic lights were working. So the already congested streets in India were even more congested. None of the trains were working, so people were just stuck at train stations, unable to go home. And I'm not saying that this is going to happen in the US. Our population density is nothing like what it is in India. Also, our population isn't growing at the rate at which theirs is at the moment. And finally, our grid system that we have is significantly more stable. But having said that, though, given that the amount of energy we're using on a daily basis is going to continue to grow, we need to be able to preempt that and be working on alternative energy solutions. One of the problems that really triggered this in India was also related to their weather this summer. So I do want to touch a little bit about climate change. I'll admit that I'm not a climate scientist, so I'm not going to go on too long about this. But one of the problems in India was that their summer was particularly hot this year, and the monsoon season came a lot later than it usually does. That meant that everybody was using air conditioning a lot more, and that added to this problem. So to touch on the issue of climate change, I just want to show you this graph right here. This picture I've taken from the journal Nature was published a couple of years ago. And a group of scientists from 27 institutions around the world sat together and came up with what they called a safe operating space for humanity. So what they did is they looked at different aspects about our environment, so climate change is up here, also looked at ocean acidification, looked at how much ozone depletion is going on, and they looked at all these other things and came up with a safe operating space. And then what they said about the safe operating space is, as long as we stay within that zone and we make changes within that zone, we're still in a reversible situation. We can go back to where we were before. But if you go past the safe operating space, what happens is we're in a place of irreversible damage. We can't go back anymore. And so the green circle right here corresponds to the safe operating space, and the red wedges that you see are showing where we are right now. So for some of the things, we're still doing okay, like ocean acidification, we're doing okay. The amount of land that we're using, we're also doing okay. Freshwater usage is fine. But then other things like biodiversity loss, we're way off the charts. Nitrogen cycle, how we use our fertilizers, again, we're way off the charts. And again, climate change, we have reached a point of basically of no return. And that, I know that there are some skeptics out there, but I personally do believe that it is caused by us. If we just quickly look at the atmospheric CO2 levels, this is just plotting thousands of years. And admittedly, there have been times when the CO2 levels have been high. But if you look at us right now, we're at the orange tip right here. We have reached levels that we have never, ever reached before. And it's no accident that this sudden increase started around 1950, which is when we really started to industrialize. So whenever we're looking at energy solutions, not only do we have to have the capacity to provide more electricity, but we also need to be doing it in a sustainable manner, and that's one of the projects that Hugh just mentioned is about. So keeping that in mind, I just want to quickly go through the different types of solar cells that are out there, and then finally talk about why both Hugh and I are working on these solution processable devices. So the typical one that you'll see out there on people's rooftops, the Seattle parking meters have them also. They're based on these silicon devices. And in a lab setting, you can get an efficiency of up to around 25%. Other types of devices that are out there, Hugh also mentioned this, the multi-junction devices. You get significantly higher efficiencies of around 40%. And then you get to the type of devices that we're working on, solution processable devices. And we can get around 10 to 15% based on those right now. So the question is, why are we working on the lowest efficiency device? And as Hugh mentioned, it all comes back to a matter of cost. So I just want to break down how these devices are made so that we can make an actual comparison of where the cost comes into play. So first of all, looking at how a silicon device is made, you start off with a silicon wafer. And I don't have this on the slide, but making the silicon wafer in the first place to make it as pure as possible is a very high energy intensive process that requires a lot of steps. So getting the material in the first place is expensive. Once you do that, there's multiple steps, including texturization and then doing a hydrofluoric acid dip. That's really not, it's a very toxic, dangerous chemical that you don't want to be using. Next step, PECVD, plasma enhanced chemical vapor deposition. That's again another high energy intensive process and keeps on going. All the steps, you use a lot of energy to do this. So that means using expensive equipment to do that. So if we look at the costs here, that means that, well, the materials cost themselves, it's about 80 cents to about $1 per watt. And Hugh mentioned that our target goal is actually 50 cents per watt. So even the materials cost is already beyond that point. But then if you think about the amount of money that you have to put in for the equipment, that comes to about $1.50 per watt. But 1 watt of electricity is not a useful amount of electricity to be making. Ideally, you want to have a plant that can create about 500 megawatts. So if you take that into account, that actually means that we have to put in about $700 to $800 million to come up with a plant that can make all these silicon devices. So an expensive problem. But if you look at the solution processable devices there, so the idea is that we'd have something like an inkjet printer or something to just print out all the materials that we have. So in Hugh's case, he's talking about using nanocrystals. In my case, what we're doing is we're actually using polymers. But if you were to do this and make these devices, none of the steps are very particularly high energy. The equipment that you can use is quite cheap. So what that means in terms of cost is that for the materials cost, we're talking about 5 cents to 10 cents per watt. So significantly cheaper than the materials cost for silicon. I don't actually have the number for the capital expenditure that will have to go into this, but at least the numbers I've seen being thrown around is at least an order of magnitude lower than what I've seen for silicon. So overall, a significantly cheaper solution. But as I said, it's not just an issue of cost. We do need to worry about sustainability. And in order to think about that, well, there's 2 things that you need to consider. One, Hugh mentioned already, one where you think about where the material is coming from, where the raw material comes from, and where it's going to end up. So thinking about the cradle-to-cradle solution. But another thing that we have to think about is that all of these processes, you need to put energy in to make the device in the first place. So if we have to put in more energy than you're going to get out, that's a useless solution. The energy you get out has to be bigger than the amount of energy you put in to make the device in the first place. So to address this issue, what people talk about is what's known as the energy payback time. And that's defined as being the time needed to operate the solar cell in the first place to recover the energy that you put into it to make it in the first place. So just looking at the different types of devices, for crystalline silicon, which is the one you see everywhere, the energy payback time is estimated to be about 2.5 years. But if you look at our solution process devices, depending on the efficiency that we're talking about, this number does change. But in the case of our solution process devices, we're talking about half a year to about a year. So less than that for silicon. But again, we want to be producing a lot of electricity, and we're talking about, for the US consumes 3.3 trillion watts of energy. And so just as an argument, I'm going to target trying to create 1 trillion watts of energy using these solar cells. So if you make the number of solar cells that are needed to get 1 trillion watts of energy, in the case of silicon, you end up having to operate the devices for 40 years to get back the energy that you put in the first place. So a very long time. In the case of our solution process devices, that numbers go back significantly. It'll take us less than 10 years to get that energy back. But this is based on the assumption that we put 100% of the energy that's coming out of the solar cell back into the problem. And that's not a realistic assumption to make. Ideally, we want to use the electricity for something else as well. So if we just make the assumption that this time we're going to use 50% of the energy back into the device manufacturing. And if we do that, then the numbers are even bigger. For silicon, now it's going to take us close to 70 years. And I don't know about you, but I don't have 70 years to be waiting. Whereas for these solution process devices, it's still about 10 years. So when we're thinking about sustainability, these solution process devices have another advantage. It's not just an issue of cost, but also to do with the issue of sustainability. So I've been throwing around this term polymer for a while. So I just want to take a step back, talk about what a polymer is and what we're specifically doing in our research group in order to make these polymer solar cells better. The basic definition of a polymer is a very long chain molecule that consists of smaller repeat units, and the repeat units are called monomers. So just as an example, showing you polystyrene, which is a very commonly used polymer. It's the polymer for styrofoam. You start off with your monomer, you connect all of them together, and you end up with this polymer chain. So the way to think about it is like you start off with macaroni, connect the macaroni together, and you get a longer chain like spaghetti. And if you mix all these longer chains together, you get a lot of chain entanglement. And it's this chain entanglement that simultaneously gives you strength to the material while providing flexibility. And it's this unique combination between strength and flexibility that allows polymers to be used in a variety of applications. So just looking around at how polymers are used, I think most people think polymers are plastics, and that is true. Plastics are made of polymers. So like oil, water bottles, and all your clothing as well. Any item of clothing has fiber in it, which is made of a polymer. But people think polymers, plastics, they must be bad for the environment. But actually, a lot of other things are made of polymers. So just as an example, DNA is a type of polymer. Other things like proteins are made of repeat units of amino acids, so that's a type of polymer too. So increasingly, they're being used in more biological applications. So polymers are not all bad. In fact, we exist because we're made of a polymer. But I can't just take one of these materials and put it in my device and expect to make a solar cell out of it. Like all of these polymers are actually insulating materials. If I put an insulating material in a device, I'm not going to get electricity out of it. So in order to address this, I'm going to start showing you some molecular structures, and I'm really hoping I'm not going to scare you off. But first of all, I'm showing you a structure of one of the most simple polymers that are out there, polyethylene. It's the polymer that's used for your plastic bags. But if you look at the structure, all you have is carbon and 2 hydrogens coming off it. So CH2, 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 all along the polymer backbone. That's all there is to polyethylene. But if you have polyethylene, then you end up with these transparent films that you can make plastic bags out of. And it's still insulating. And in order to make it semiconducting, what we actually go through and do is that instead of having single bonds between all these carbon atoms, we place double bonds between every other carbon bond. And this really simple change that we can make allows electrons to be delocalized along the polymer backbone. And then instead of having this plastic film, now you can end up with a film that looks like a metal. It shines like a metal. Pretty much, well, if you look at it, it looks like a metal, but it's a polymer. And this simple molecular engineering that's done right here, it might look simplistic and it might look easy. But at the time that people discovered this, it really was a revolutionary idea. The 3 people that developed this idea in the late 1970s were awarded the Nobel Prize for Chemistry. And since then, this whole entire new field of semiconducting polymers has truly exploded. Now we're able to make a lot more complex structures. So instead of just having carbon and hydrogen along the polymer backbone, we can introduce all these other elements in them. But the same motifs is still there. Alternating double bond, single bond, double bond, double bond, single bond, double bond causes delocalization of electrons. We now have a polymer that can conduct electricity. But we also can start to tune the color of the light that it absorbs, no longer just black, but we can tweak the color it absorbs, and we can tweak the color of light it emits. And so just right here, these are some of the polymers that we've made in our laboratory, and you can see that they're extremely colorful materials. And so using the ability for them to emit light, they are now actively used in commercially available devices as LEDs. So just as an example, Sony is actively developing flexible displays to be used. A lot of camera companies actually incorporate these organic LEDs into the digital camera screens that you have. And then finally, the latest Samsung Galaxy phones that are out there, they actually have these polymers in them. So as Hugh mentioned, an LED works by you put charges in, charges combine, and you get light coming out. That's what an LED does. And what we're trying to do in these photovoltaic devices or solar cells is to do the exact reverse. So absorb light, split the charges and get them out. So that's all we're trying to do. So with that in mind, in order to improve the efficiency of the existing polymer devices, what we need to do is to improve every single step in that operation. So first step, remember, light absorption. Second step, separate the charges. Third step, get the charges out. So with that in mind, whenever we're designing polymers in our lab, these are the criteria we're following. The polymers that we make have to have good absorption in the visible region. If it doesn't, we're just not going to get the sunlight in. Second step, to get the charges dissociated, we need to do some energy level engineering. Third step, charge extraction. So the materials that we make have to have high charge mobility. And then finally, the thing that keeps the cost of these devices low is that we can do things like inkjet printing. For that, it means that we need to be making polymers that are soluble in common organic solvents. So this list sounds easy enough, but it's actually been very hard for us to achieve, because what usually happens is when we improve one thing about the material, we end up destroying something else. So for example, for a long time, making a material that absorbed a lot of light meant that we would end up reducing the charge mobility, so the efficiency would go down. Other things like the way that we make polymers that are solution processable, we actually add a lot of insulating chains to the polymer backbone. So that meant that, again, if you're adding insulating material, your charge mobility goes down. So we've had to do a lot of optimization in our research group, and others around the world have had to do this as well. So I'm just going to quickly show you one example of a polymer that we published recently. I'm not going to go through it in detail, but I just want to show you sort of how complex the polymers we make are now. We can really do some serious molecular engineering and get the structures that we need to make using organic chemistry. So just to go through some of the aspects here, in order to make something that can absorb a lot of light, we use special monomer combinations that we know we can move around in order to improve the light absorption. That also allows us to control energy levels so that we can efficiently separate the charges. The third thing I mentioned was charge mobility, and having these planarized fused ring systems allows us to increase the charge mobility. And then finally, these chains that we have on either side, I mentioned that you need to add insulating chains to improve solution processability, so we've added that. And after all this engineering, what we can do is get a pretty good efficient device out of this. So just looking at where we're at as a field for polymer solar cells, right now, Mitsubishi Chemicals has the championship device for single junction devices, where we can get an efficiency of 10.1. And if you can make a multi-junction device, then that efficiency goes up to 10.6. At the University of Washington, we can get to around 8%. So we're not quite up there, but we are pretty high in the competition. So just to wrap up, I just want to show you that these solar cells are really promising. And there are a couple of startup companies that are out there. For example, a company called Plextronics in Pittsburgh, they have the facility to really print out these solar cells already. There's some interest in these solar cells from the military, because having something that is so lightweight and flexible is an advantage instead of having to carry these heavy battery packs around. Similarly, for developing countries where their grid system isn't developed at all, it's great to have a portable device. And then finally, if you ever have the chance to go to San Francisco in the Mission District, their bus shelters out there do actually have these polymer devices. So if you see something red, that's an indication that it is a polymer device. So just finally, I'm going to cover the grand challenges that we have for our particular classes of materials. Like Hugh said, one of our biggest problems is also defects. Polymers are intrinsically messy. What gives them the flexibility also reduces its electronic properties. So understanding how you can control that is one of the active areas of research that we're working on right now, sort of perfecting the polymer synthesis strategies that are used. The second thing is, as I mentioned, the flexibility of the polymer is one of its actual killer things about giving its correct electronic properties. So one of the things that we need to be doing is making the polymer a bit more silicon-like. And that includes things like increasing the dielectric constant of the material and making something that's more rigid so that there's less energy loss pathways. Final thing that needs to be addressed about polymers is the stability. People have done some accelerated lifetime tests that suggest that these polymer devices should last more than 10 years. But that is still something that needs to be considered, and that's what some people are looking at.